All right, hello everyone, and welcome to lesson 1.7. We're going to be talking about the intermediate value theorem and doing a little bit of review given that our Unit 1 exam is coming up very soon. Let's go ahead and get started. I've thrown on here two questions that I've used previously on Unit 1 exams. I'm going to go ahead and do those two do now questions right now and then answer the questions that pop up on the nearpod. All right, let's take a look. Remember, the first thing we do when we're evaluating a limit is first try to use direct substitution. So with direct substitution here, if we plug in -1, we'd have 8 minus 3 minus 1, right? Because I'm plugging -1 cubed, that'd be -1 in there. Will give me a value of 4, so 4 through direct substitution. Now over here, if I do direct substitution, I'll find I get 0 in the numerator, and down here I would get 0 in the denominator, so I need to do some work here. Remember, you got to keep your limit notation all the way through. We don't want to drop that. We're taking a limit here until we do our direct substitution. So my limit as x approaches 3 is going to be equal to x minus 3 over the factored form down here, which will be x minus 3, and x minus 2, which is going to give me the limit as x approaches 3. Limit as x approaches 3 of 1 over x minus 2, which now when I do my direct substitution, I'll get 1 over 1, so my limit is 1. All right, limit is 1 there. Okay. So that was just a quick review for limits. Today we're going to wrap up with one final topic, our last topic of this unit, but also a very important one of the first major theorem that we'll see this year in AP Calculus, which is called the intermediate value theorem. All right, let's take a look. We're going to keep in mind one crucial idea that we've already seen before, which is that continuity means connectedness. If something is continuous, it is connected all the way through points. So let's think about this question here. Is it possible to draw a continuous function from A, which is down here, to B, which is up here, without passing through the line y equals 1? Now the line y equals 1, remember, is infinite, so it continues infinitely to the left and infinitely to the right. All right. Can I draw from point A to point B continuously without crossing through this line? If you pause to think about that for a second, you'll realize, no, if we're going to have a continuous function, that means I can't pick up my pencil. If I want to get up from start to finish, from point A to point B, there's no way around it. I'm going to have to pass through that line somehow. Maybe that path, maybe it does something like this. No matter what, even if I do a non-function path, I'm going to have to pass by that line, no matter what I do. Remember, this line continues infinitely. So this actually leads us to an interesting conclusion. Let's tease that out some. Given that f of x is continuous, let's say that f of x is continuous, and f of 2 comma 5, so not this specific graph, but f of 2 comma 5 exists, and f of 4 equals f of 2 equals 5 and f of 4 equals -3. Which of the following things do we know? Remember, this function, this new function we're going to think about, is continuous, and we know 2 points. In other words, we know f of 2 is 5. So I'm just going to put a point here. F of 2 is 5. That maybe is up there. 2 comma 5. And f of 4 is -3. It's going to be like down here somewhere. So I'm going to say like 4 comma -3. What things do we know? Do I know that f of 3 is 0? F of 3 would be somewhere in the middle here. No, I don't actually know that for sure. I'm not given enough information. But it could be. I don't know. All we're given is 2 points and the function is continuous. So I don't know. Maybe the function f of 3 equals 0. Could be true. Maybe f of 3 is 0, right there on the x-axis. How about f of c equals 0 for some c, where c is some x value? In other words, does there have to be some x value where the function is 0? Yes, it does. If I'm going to go from an output value of 5 to an output value of -3, does there have to be some place where the output value is 0? Yes. If I'm going to go from a y value of 5 to a y value of -3, I have to have some place where the output value is going to be 0 if the function is continuous. That's key here. So do we know this? Yes, we do. There has to be some place where the y value is 0 if we have a continuous function, going from 2, 5 to 4, negative 3. How about f of d equals 1, where d is some x value? Well, that also has to be true, right? Because if the y value starts at 5 and the y value or output value ends at negative 3 and the function is continuous, do I have to pass through a y value or output value of 1? Yes, to go from 5 to negative 3 continuously, we have to cross 1. Again, we don't know what that function would look like. It could go up and then down and then back up. It could go straight there. It could do lots of things to get there. But ultimately, this function, this continuous f of x function, is going to have to cross a y value of 0. That was part B. And it's going to have to cross a y value of 1. If it's a continuous function, it's going to have to cross through those. And that ultimately leads us to our big conclusion here, which is the intermediate value theorem. The intermediate value theorem says this: a function y equals f of x that is continuous, and that's the key here, the function has to be continuous on a closed interval a to b, takes on every value between f of a and f of b. We can say inclusive because f of a and f of b, so if it's continuous on the closed interval, f of a and f of b also exist. What does this mean graphically? Well, if we know some point on the graph f of a here, and we know some point f of b on the graph over here, and the function's continuous, it's going to cross through every y value between f of a and f of b. It's going to cross through all of the y values that are stuck between them. Maybe the graph also crosses through some y values above it or below it, but we don't actually know. If all we know are 2 points and the function is continuous, we know that it passes through each of those y values at least once. That's all we know. This graph, if we know point A and point B, will cross through all of the y values at least once if the function is continuous, the y values between f of a and f of b. We don't know about stuff above or below or how many times it crosses through those y values, but it will cross through all of those y values between f of a and f of b if the function is continuous. Again, that's key. So what if we want to explain using the intermediate value theorem how you know that f of x has a 0 on the interval 2 to 4? Well, the nice thing about the intermediate value theorem is this: if we can establish that f of x is continuous and find some points on the graph, sometimes we can make some conclusions. All right. So let's just see what happens. What is f of 2, since that's our end boundary here? Let's find f of 2. Well, f of 2, if I substitute that in, will be 4 minus 8 will give us negative 4 plus 3 is negative 1. All right. If I plug in 4, I'll get 16 minus 16 plus 3 is 0. So plus 3 is 3. So f of 4 is 3. So look at this. Our starting point is actually a negative output value, and our ending point is a positive output value. So does there have to be a 0 between f of 2 and f of 4? Yes, if the function is continuous. So let's look at the function. Oh, it's a polynomial. That means it's continuous. So yes, this is a continuous function. F of 2 is negative 1. F of 4 is 3. Therefore, there has to be a 0 between 2 and 4 because the y values need to change from negative to positive. Now, how do we write this out in a mathematically rigorous way? All right, this is what we're going to do, and I would actually just encourage you to just go ahead and absorb and memorize this, because this is ultimately like something we'll do a lot, and if you can just file away this sort of sentence structure for the intermediate value theorem, it'll help a lot. So let's go ahead and do this. All right. First, we have to establish that the function is continuous. So I'm going to say f of x is continuous because it is a polynomial function. If you can back it up with how you know it's continuous, that's better. So we state the requirement: f of x is continuous. Next, we can go ahead and say f of 2 equals negative 1 and f of 4 equals 3. So we state the function is continuous, then we state the boundaries here. F of 2 is negative 1 and f of 4 is 3. Then we can say, therefore, by the we'll go ahead and we can capitalize it just to make it important. Intermediate value theorem. there must be a value of x between x equals 2 and x equals 4, for which f of x equals 0. So that's how I want us to write this out. F of x is continuous because it's a polynomial function. You state the function is continuous. You have to do that. Then you state the endpoints. F of 2 is -1 and f of 4 is 3. Therefore, by the intermediate value theorem, there must be a value of x between x equals 2 and x equals 4, for which f of x equals 0. You will sometimes also see people say this. There must be a value of x called c between x equals 2 and x equals 4, for which f of c equals 0. That is also acceptable. Since we're asked about zeros here, we can say then, therefore, f of x has a 0 on 2 to 4, and we can just restate the question there. Ta-da! And there we go. So it does require you to write out these sentences when we're talking about intermediate value theorem things. You got to state the function's continuous, and you got to state the endpoints here. Then cite the intermediate value theorem. All right. So you can say given f of x is continuous for all x, and below is the table of its values. Some trouble here. There we go. Given f of x is continuous for all x. Okay, so we're told the function's continuous. That's convenient. And below is a table of its values. Again, certain values. We know the function's continuous, so it actually exists at all of these x values, even between these points, but a table of its values down here. And what intervals must f of x have at least 1, 0? How do you know? So let's track, oh, that should be a lowercase f, I apologize. Let's go ahead and track then. If it's got to have zeros, that means our output values have to change from positive to negative or negative to positive. So it looks like we have one place where our f of x value changes sign. So we have to have a 0 on there since our function is continuous. So positive to negative, negative, negative. Oh, we're back to positive. So we have to have a place where f of x crosses 0 there. Positive, 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 and then negative again there. Okay, so it looks like we have 3 places where f of x has at least 1, 0 for sure. Could there be other ones? Yes, because we don't know all the other intermediate points, but we have at least 3 zeros that we can prove. So we go back and we do our intermediate value theorem thing. All right, so we say f of x is continuous. And we can shift this one slightly. We could go ahead and do the exact same thing we did above and like actually cite the individual values. Or we could say f of x is continuous. And then we can say, what would be the best way here? And we'll go ahead and use the same structure we did last time. Let's say f of -5 equals 4, and f of -3 equals -2. Sorry. And we go ahead and state the next interval. F of 1 equals -1, and f of 3 equals 5. F of 7 equals 6, and f of 10 equals -2. Therefore, by the intermediate value theorem, f of x has at least 3 zeros. We can say since f of x changes sign at least 3 times. That could be a way we back it up there. So again, we state that the function is continuous. We state the facts that we know, so we know these intervals, or these points. Therefore, by the intermediate value theorem, f of x has at least 3 zeros since f of x changes sign at least 3 times. And if we really want to back this up, we can say on, and then we can state the actual intervals. -5 to -3. 1 to 3. And 7 to 10. There we go. All right. Cool. Let's take a look next. All right, I want you to pause the video right now and go ahead and answer 4a and b. Given that the function h is continuous for all x values, and h of 7 is 9, and h of 10 is -2, if c is some x value and f of c equals 3, c must lie on which interval? What can we prove here? Go ahead and answer that one. And then b, I think there are 2 zeros on the interval 7 to 10. Given the information above, can you prove that there are 2 zeros? Why or why not? Go ahead and pause the video and give those two a shot. All right, cool. Let's start with A. It actually might seem a little overly simplistic here. We're told that the function h of x is continuous, so IVT will apply, and it's okay to abbreviate the intermediate value theorem IVT. And we're told these 2 points, 7, 9, and 10, -12. So we can already tell, actually, if we're talking about the IVT here, the interval we're interested in here is the interval 7 to 10, right? Or if we don't include the endpoints because we know them, we could say 7 to 10, non-inclusive of the endpoints there. All right, and that ultimately ends up being sort of our key into this. If c is some x value and f of c equals 3, c must lie on which interval? Well, if we know the points on this continued function go from 9 to -2, that's our output values, and we know we have an output value of 3, then that means what can we prove? We can prove then, or we know for a fact, that this point c has to exist on the interval between the x values of 7 and 10. So we're going to go ahead and say this here. 7 to 10, because we know h of 7 is 9 and h of 10 is -2. If we have an output value of 3, that's between outputs of 9 and -2, so our x value has to be between 7 and 10. So there you go. B, I think there are 2 zeros on the interval 7 to 10. Given the information above, can you prove that there are 2 zeros? Why or why not? And this is actually one of the key things from the intermediate value theorem. The IVT applies to function h of x because it is continuous, but the IVT guarantees only one output value. It cannot prove that a specific output occurs more than once. Basically, we assume the straight line scenario from point A to point B. We can only prove that it crosses through all the outputs once. We actually cannot state how many times it crosses through each output. So the IVT applies to function h of x because it's continuous, but the IVT guarantees only one output value. Oh, that's a weird way to say it. Guarantees only sorry about that, that each output value occurs once. That's how we should say that. The IVT applies to function h of x because it is continuous, but the IVT guarantees that each output value occurs once. It cannot prove that a specific output occurs more than once. There we go. All right, go ahead and try practice problems 1 and 2. Pause the video, give those a shot, and come back and check your answers, please. All right, let's take a look. Explain why you cannot use the intermediate value theorem to prove that g of x equals 1 over x has a 0 in the interval -2 to 2. Well, think about it. If you plugged in g of -2, you would get -half, right? And if you plugged in g of 2, you would get +half. So you go, well, wait a minute. Doesn't this show that there is a 0 then between -2 and 2? Well, wait a minute. We know for the IVT to apply, the function needs to be continuous on the interval we're investigating. Is 1 over x continuous on the interval -2 to 0? It is not. We have a point of discontinuity at x equals 0, and that is on the interval. So our IVT theorem actually does not apply here. So we can go ahead and say that. The IVT does not apply to function g of x on the interval -2 to 2 because g of x is not continuous on -2 to 2. And there we go. Therefore, we cannot apply the intermediate value theorem in this case. If you want to be more specific, then we can go ahead and state that g of x is not continuous on -2 to 2 and has a point of discontinuity at x equals 1 or x equals 0, and that's the problem. That's why it's important to check continuity before you use the IVT. All right. 2. Does h of x equal 4 sine of x minus 3 have a 0 in the interval 0 to pi over 2? Well, we can do some investigating here. Let's just start with the endpoints. H of 0. H of 0, if I plug in 0, it's going to give me 4 times the sine of 0. 4 times the sine of 0. Sine of 0 is 0. Minus 3 is -3. And h of pi over 2, that'd be 4 times the sine of pi over 2. Sine of pi over 2 is 1. So that's 4 minus 3, which is 1. So it looks like the IVT can be used here to show that we have a 0 on the interval. The next thing we need to show, though, is do we have a continuous function here? So let's see. The only really interesting thing here is the sine of x. It's the only variable thing, but sine functions are continuous. Sine functions are continuous, right? So the IVT will apply. Sine functions don't have any, holes, gaps, other things going on here. Removable discontinuities, infinite discontinuities, anything. So I can say h of x is continuous. I state my points then. H of 0 equals -3. And h of, I'm going to spell out pi like that, pi over 2 equals 1. Therefore, by the intermediate value theorem, there must be an x value called c on the interval 0 to pi over 2. Such that f of c equals 0. There we go. We state the function is continuous. We state the endpoints. Therefore, by the intermediate value theorem, there must be an x value called c on the interval 0 to pi over 2, such that f of c equals 0. H of x has a 0 on that interval. If we just want to go ahead and sort of beat a dead horse here, it's not too bad to just repeat yourself there to answer the question. There we go. Now, some of that can be useful in these situations as we get into more complex stuff. Is an acronym here that can help you keep track of different ideas in these more complex situations. Some people say, like, you got the goods, and this is something that the Stanford engineering departments use too. The acronym I'll do it this way, GU, I'll extend this down, GUDES. If you got the goods, you talk about the givens. What is given? In this case, we're given a function and our interval here. What are our unknowns? In this case, we don't have a ton of unknowns, but we do realize the thing we need to justify is there a 0, right? Then we can make a diagram. In these intermediate value theorem questions, actually making a diagram can be kind of useful, as we'll see here in a second. Then we write out any equations that we might need. In this case, we do not need equations, and then you solve, all right? Now, this sort of structure is not always generally applicable to like every situation, but think of them as almost like tools, right? If you get to a situation, maybe there's not a ton of givens that you have to list out. In this case, we have an equation and an interval. There's not really unknowns, but a diagram could be useful, right? If you're stuck on what to do and you have some points, let's just diagram them out and maybe it, cues your mind. 0, -3 is down here. Pi over 2, 1 is maybe up here, and you might go, hey, is there a 0 in the interval? Well, there has to be, and I can see it visually now from my diagram. So think of this almost as like a checklist of things to use to help solve more challenging problems. Sometimes this year we'll actually use all of these in order to solve the more complex situations that might arise. All right, we're going to wrap up here. I'm going to go ahead and do problems 1, 2, and 3. Pause the video, do problems 1, 2, and 3, and then I'll go through and you can check your answers against mine just as practice getting ready for the exam. All right, go ahead and do that. All right, here we go. Let's wrap up with the little practice problems here. We have a function, the graph of g of x. Oh, so this is the function of fx. That's interesting. Over here is the graph of g of x, though. Maybe that's worth labeling, g of x. And we're told to evaluate this limit. Well, we know some limit rules. We can actually break this limit up into 2 times the limit as, oh, why did I do that? I double wrote the limit. That's interesting. 2 times the limit as x approaches 0 of f of x plus the limit as x approaches 0 of g of x. Remember, you can break up limits algebraically like this. The limit applies to both the functions. We can factor out the 2 and now take care of the limit separately. The limit as x approaches 0 of f of x, that's easy. If we plug in 0, we just get 1, so that's 2 times 1 plus the limit as x approaches 0 of g of x. We got to go to the graph here. As x approaches 0 of g of x, it looks like our limit approaches 1. So this ends up being 2 times 1 plus 1, which will give us 3. All right. So now we have h of x given here. We have k of x, which is x squared, and we want to evaluate the limits down here. All right. The limit as x approaches 3 of h of x. Well, h of x is just this function here. That's not too bad. It's a linear function as x approaches 3 of 2x plus 1. I plug in, and that'll give me 7. Right? That was just we were able to do that by direct substitution. All right, let's take a look at b. B things look to be a little more complicated, okay? The limit as x approaches a of h of x. So we're still using this first function up here. This is interesting. Let me just go ahead and write this out by plugging things into that function notation. So limit as x approaches a, I'm just going to leave that. I don't know what a is. It's just some placeholder right now. H of x. H of x is 2x plus 1 minus h of a. So this is its own quantity. I'm going to take h. I'm going to plug a in, right? I'm going to take h. I'm going to plug a in. So that's just going to be 2a plus 1. Notice I put in parentheses. If you want to, we can actually put both of them in parentheses so you can see h of x minus h of a over x minus a. All right. Let's clean some of this stuff up and see what happens. So this is going to be the limit as x approaches a of 2x minus 2a when I distribute. So that I can't do a whole lot with. But then I have 1 minus 1 when I distribute, right? So that'll actually make the 1 minus 1, that'll go away. So I end up with 2x minus 2a in the numerator over x minus a. I can see some things factor here. So that'll be the limit. Notice I'm carrying my limit sign all the way through. You have to do that. Factor out the 2, so I end up with x minus a over x minus a, and voila, our x minus a's will cancel out, and I'll be left with simply 2. This is actually a derivative. We just found a derivative, all right? Derivatives really are just limits, and we'll return to derivatives next unit. You don't need them for this unit exam, but we teased them already at the very beginning of the year. Now we're seeing them again. All right. Let's take a look at one more thing here, limit-wise. All right, this limit here, we can do something similar. We're going to take k's, and we're going to evaluate k, which is up here, by plugging some stuff in. So this is the limit as h approaches 0 of k of a plus h. So I'm going to take what k is. I'm going to plug a plus h in for x. So a plus h squared. A plus h is substituting in for the x squared. Minus k of a, so I'm going to plug a in for x. That's a squared over h. I didn't take the time to do it last time, but we should have pointed out for b there that if I just substituted in a for all the x's, I'd end up with 0. So h of a minus h of a, 0 over a minus a, 0. 0 over 0. So we had to go through those steps last time. Similarly here, if h is going to 0, I end up with a squared minus a squared over 0. So we get 0 over 0. So we have to do some creative factoring and stuff here. So let's do that. Limit as x approaches 0. A plus h squared. Let's factor or FOIL all that out. That'd be a squared plus 2ah plus h squared minus a squared. I just FOILed out a plus h squared all over h. Notice my a squareds will cancel out. And I'll be left with the limit as x approaches 0 of 2ah plus h squared over h. We could factor out an h and cancel stuff out, but I'm going to speed this up. That h will cancel out with that one and one of those. And I'll be left with the limit as x approaches 0 of 2a plus 1h left over. As, ooh, my h's became x's. I apologize for that. That should be an h. That should be an h. That should be an h. As h approaches 0, h goes to 0, and that leaves me with just 2a. This is actually also a derivative. We just found another derivative, and the limit is 2a. And the last one to clean up, using the definition of continuity, determine if f of x here is continuous at x equals 3, and justify your answers. Remember, there are 3 things you need to do for continuity. First, we need to make sure f of 3 exists. So let's come down here. If I plug in 3, f of 3 would take this, go into the bottom branch here, because it takes x is greater than or equal to 3. And I plug 3 in there. F of 3 is going to give me e to the 0, which is 1, plus 6, so 7. So f of 3 exists. We also need to make sure that the limit exists. So we need to make sure that x squared minus 2 equals e to the x minus 3 plus 6 at x equals 3. So that would check for us the limit, because remember, we checked to make sure the point exists. Now we're checking the limit, and if the limit exists at this breaking point here, the left side and the right-hand side have to be coming together. So if I plug in 3, that'd be 9 minus 2, which is 7. My computer's lagging a little bit. Good thing we're at the very end here. 9 minus 2 is 7, equals. If I plug in 3 here, I get e to the 0, which is 1, plus 6, which is also 7. So that should be a check mark. We now know that the limit exists. And now I can start making I'm pretty close to be able to make my conclusions. I now know f, let's actually do, we can type this. It'll probably be faster. Oop, let's back that up. All right. We may be too lagging here. I may have to just kind of talk through this. All right. Cool. So we now know that the point exists, f of 3 equals 7. We now know that the limit exists. And we are having some trouble. Here we go. You would write this out in limit notation, but at the same time I'm going to type it so my computer can handle it. We would say that the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right, which equals 7. All right, and we just write that out in limit notation. I'm saving time so my computer can handle it by typing it. So we now know that f of 3 equals 7. The limits the limit exists, and it is 7 as well. So we can say, therefore, the limit as x approaches 3 exists. And then remember, the third thing we have to do to prove continuity is state that the limit equals the point, and we are finished. All right. So step 3 here. We'll go ahead and put we'll type that in too so we can speed things up. Step 3 here is that f of 3 equals the limit as x approaches 3, which equals 7. Therefore, f of x is continuous at x equals 3. All right. Sorry about the delay there. Those are 3 things you need to do. You need to make sure that the point exists, that the limit exists, so you check it and you have to state it. Therefore, the limit as x approaches 3, that should say as x approaches 3 exists. And then we need to make sure that the actual point f of 3 equals the limit. And therefore, if that is true, then the function is continuous at that x value we're checking. All right. Cool. Make sure you complete the rest of Nearpod, and don't forget that you can come by to review for the unit exam starting, or actually, I guess tomorrow afternoon, Wednesday afternoon. Don't forget there's also ways you can study. You can use the practice tests. There's the IBT and continuity worksheets that'll be posted online. You got the Unit 1 student packet. You got your sets that you can do. There's plenty of ways to study, or you can come study with me Wednesday afternoon at 3:30. Okay? I'll talk to you all later. Good luck.